All right, in this example, we're competitor and survivor, and our challenge is to beat the other team in a running and rowing race. Okay, so we've got a boat on one side of a riverbank, and we need to basically get across the riverbank and down the river. And we have specific measurements there. So let's just draw out the situation. We've got our river, and we are somewhere. Let's just say here. It says that you must row across a 200-meter wide river. So I'm just going to draw 200 meters like that. All right. And then the shore is 500 meters in length. So something like this. And what do we know? We know that we can row at 1 meter per second, and we can run at 2 meters per second. So the real question is, when we're looking at this, should we just basically row all the way? But rowing's pretty slow, we know. Or should we just go straight across and then, since we can run faster, do that? But then we're going a further total distance. So the idea is, what angle should we row at? So we don't have to row for too long, but then we minimize the distance we're going. And there's going to be some best path to take that will help us to finish as fast as possible. So that's the question. So let's figure out how to set this up. So to set this up, what we're going to do is we're going to figure out a couple of variables. Well, really just one variable. We just want to know what distance we're going to run, let's say. So the distance we're going to run, we are going to represent with the variable r. So let's just switch things up a little bit. So let's just to use x and y, just to be using our familiar variables, let's let x represent distance rowed. We'll start with that since that's the first thing we're doing. So I'm going to label that just going to be the hypotenuse there. That's what we're rowing. And then we've got that right angle triangle. It would be nice to know what's the top portion of that right angle triangle. So I'm just going to label that y, that top portion. And then the leftover portion, I'm going to take away the river. The leftover portion would just be 500 minus y. And what is y actually representing? Well, in this case, it's what we're not running, actually, because we're rowing up to that point and then we're running the leftover part. So let y represent distance not run. So it's a little backwards, but just in terms of the diagram, it does make the diagram a little neater. Okay, and in the end, what do we care about? We care about how long this takes. So we're going to need a time variable. So let t represent the time in seconds. And actually, the other one should be in meters, so I'll just put that in brackets. Okay, so let's go ahead and figure this out. So we've seen that if we're dealing with distances and such, it's handy to remember v equals d over t. Velocity or speed equals distance over time. And what do we know in this case? We know our speeds. We know potentially what our distances are, and so we can figure out the time. Okay. So what we want to really figure out is we want to minimize the total time. And to do that, we're going to have to know what the time rowing is plus the time running. So let's figure out those two times. So the time rowing, well, how far are we rowing? We're rowing a distance of x and divide that by, well, here, let's just do a quick little, if we're trying to figure out times, we know the velocity is distance over time, so time is just equal to distance over velocity. So let's say you're going 10 kilometers at a speed of 20 kilometers per hour. It would take 10 over 20, as in half an hour to get to wherever you're going. So it's always distance over velocity to figure out the time. So we have a distance of x, but we also know that we're rowing at 1 meter per second. So x over 1. And the time running, well, we're running for 500 minus y over a speed of 2. So there we have it, is our two separate equations. So we can say that the total time is just going to be x over 1 plus 500 minus y over 2. So we're in a situation where we have two variables. We need to figure out how we can get the one variable in terms of the other. And that's where that right angle triangle is going to come into play. So from the right angle triangle, the hypotenuse is x squared. And, not 500. The one side is 200. The other side is y squared. So that's why it was nice to intentionally set it up this way. Sure, it made 500 minus y feel a little odd, but this helps. So now I can just say x is equal to the square root of 200 squared, which is just going to be 40,000. Let's just get an actual number there, plus y squared. Okay. And let's just plug that back in. So t total, I'm just going to start calling it t, is just going to be x plus 500, or sorry, not x anymore, square root of 40,000 plus y squared plus 500 minus y over 2. All right, and now all we need to do is take the derivative and then see if that's the maximum or the minimum. So t prime, it's a square root, so it's just 1 over 2 of that square root, and then a little bit of a chain rule. In this case, the chain rule works pretty nicely. It's just 2y. The second one, the over 2, that's just like a constant in front, so it just stays as over 2. And then 500, well, that's nothing, so it's just negative y. So it's just negative 1. Okay. And we need to set this equal to 0. So what we're going to have is 0 equal to 1 over the, 2y over that nasty looking square root plus y squared minus 1/2. So let's rearrange, get things looking a little nicer. So the 2's are going to nicely cancel out. And let's move the 1/2 over. So y over that. And yeah, it's not going to be the prettiest of equations to solve. We're going to cross multiply, so we're going to have square root of 40,000 plus y squared equal to 2y. And then from here, what we're going to do is square both sides, since we have a square root. All right, so just do that like that, and that cancels out the square root, so it's just 40,000 plus y squared. And now on the right side we have 4y squared. And this isn't too bad to isolate for. 40,000 is now just going to be equal to 3y squared when we move over the y squared itself. And then divide by 3, so y squared, or I'll just say y is equal to 40,000 divided by 3 square root of that. And so y itself is equal to, we'll approximate it. There's a positive and a negative answer, but we only want the positive answer. We're dealing with distances here. So it's just going to be 115.5. All right, so we've got our distance not run in a sense here. We don't really care about that, actually. We just care about the time. So let's just see what the time is if we plug that back in. So time is going to be equal to, 40,000 into that equation of y, or in terms of y. Square root of 40,000 plus 115.5 squared. And that, since we had square rooted that earlier, if we keep the exact same number, it'll work out nicely. Plus 500 minus 115.5 all over 2. And if you do this calculation, what you end up getting is an answer of about 423.2 seconds. Okay, so that looks good. Now, again, we've figured out a critical point. We need to check the ends to make sure that the ends aren't the maximum or the minimum themselves. And in the case, what would the ends be for this one? Well, the ends would be either all rowing or just like minimum rowing, which would be like going straight across and run 500 meters. Okay. And this won't be too bad to actually calculate. So case 1 will be all rowing. So, well, if we're rowing all the way, what is the actual time going to be? Well, we just need to know the distance. So let's figure out the distance. Let's do another little diagram here. So we're going across 200, the river, and 500 meters down. So we just need to do a little bit of Pythagorean theorem to figure out what x would be. And then we can easily figure out the time from there. So x in this case is just going to be Pythagorean theorem will be about 538.52. And so the time, well, since we're just rowing, it's just going to be that distance divided by 1. So, well, there's no real calculation there to do. It just ends up being 538.52 seconds. So definitely slower. Now, 500 meters running. I'll just call this second option. So in this case, we're going up 200 meters and across 500. So what's happening in terms of time? Well, in terms of time, the rowing is going to take 200 over 1. So this is the rowing. And in terms of the running, well, we're running for 500 meters, and that's going to be at 2 meters per second. Run, not rum. Okay. And so then, well, that's going to be 200 plus 250 is 450 seconds. So faster than just rowing, but if we compare it to the best time, well, the best time was 423 seconds. So therefore, the minimum time is 423.2 seconds. And let's just double check. What is the question? Yeah, so how long will it take to reach the finish line? 423.2 seconds if you go across at the right angle.